Okay, great. So David Swinarski is our next speaker this afternoon from Fordham University. We'll hear about singular curves in Mukai's model of M7 bars.
Thank you, Melody. And first, I'd like to thank the organizers for putting on this wonderful conference, and also to say a special thank you. This is my first face-to-face research talk since before the pandemic, and so I'm really excited to be back in the room with all of you. All right, so almost 30 years ago, Mukai proposed a birational model of the moduli space of Deligne-Mumford stable curves of genus 7. So remember, M7 bar is a compactification of the moduli space of smooth curves. In M7 bar, you would add nodal curves that have finite automorphism groups. And an open question is to study the birational geometry of these spaces when G is larger than 3. Here's Mukai's model. He says you take the Grassmannian of 7-dimensional vector subspaces of a 16-dimensional vector space and mod out by the action of the algebraic group SO10. Okay, so let's unpack that a little bit. How is SO10 acting on this Grassmannian? By its spin representation. Okay, so SO10 has, since it's type D Lie group, it's got these irreducible representations that don't come from the tensor product of the standard representation, the so-called spin representations. For SO10, they're 16-dimensional, and that's how SO10 is acting on this GR716. Let me say a little bit more about how we get there. Okay, so in general, we know for algebraic curves how many and what type of polynomials you need to carve out the canonical embedding. So for a general genus 7 curve, you would expect that the canonical ideal should be generated by 10 quadrics. And the starting point for Mukai's construction is that he proved that for a general smooth genus 7 curve, and here general means that it's not hyperelliptic, not trigonal, and not tetragonal, that the kernel of the multiplication map from 2 elements of, in degree 2 in the canonical ideal multiplying together and landing in the 4th degree of the ideal, that multiplication map has a 1-dimensional kernel. So let's let Q be a generator of that kernel. Now you have a 10-dimensional vector space, I2, and you've got quadratic form on it. And so we should do what we always do when we have quadratic forms, namely you should study the isotropic vector spaces of your vector space I2. And so you hunt around if you want maximal isotropic subspaces or Lagrangians. It's not hard to find them. And in particular, if you look at any smooth point, I mean, here I was talking about smooth curves, and later we'll be talking about singular curves. But for smooth points, if you look at the row space of the Jacobian matrix, that's always going to be a rank 5 matrix, and then its span is going to give you a Lagrangian with respect to this quadratic form. Mukai's notation for that is WP perp. And so here's a quick summary of Mukai's results from his 1995 paper. If you map every point P to the Lagrangian given by WP perp, so the row space of the Jacobian matrix, that embeds your curve C into the orthogonal Grassmannian. So this is a variety that parameterizes 5-dimensional isotropic subspaces of a 10-dimensional vector space with this quadratic form. The orthogonal Grassmannian, in turn, via spinners, naturally sits inside of P15. And so we're able to embed our curve into P15 that way. Moreover, this spin embedding of your curve naturally lands on a projective 6-dimensional space that Mukai calls capital P, and so I will too. I realize it's kind of confusing. It's not a point, it's a P6. And so now we started with a canonical curve. We've re-embedded it into a P6 inside P15, and that is your canonical curve back. And so Mukai finishes the story by saying, All right, so if you look at the Grassmannian of 7-dimensional subspaces of P16, of the 16-dimensional vector spaces, so when you projectivize, you're looking at P6s and P15, sections of the orthogonal Grassmannian are going to give you canonical curves, and if you mod out by the action of SO10, you will recover something that's birational to M7 bar. Okay, so that's how he proposes, or that's the model he proposes for M7 bar. Let me take a few slides and just review a few of the major themes from geometric invariant theory, since I know we have a general audience and not all of you here are people who construct moduli spaces using GIT. So geometric invariant theory is a general technique in algebraic geometry. It's one of many, it's not the only way. And the goal is to construct quotients when you have an algebraic group acting on a scheme. So in GIT, here's the approach we take. So if you have a projective scheme X, for us it's going to be a Grassmannian today, and an ample line bundle on your X, we naturally have the Plücker line bundle on our Grassmannian, and you have a reductive group acting on X, for us it's going to be SO10. The GIT quotient is just proj of the ring of G invariant sections of your line bundle. Okay, so that's a ring. Because our group is reductive, it's going to be, that ring is going to be finally generated, so we'll get a scheme. But what are its properties? Okay, so here's where things get to be a little bit weird. If you're coming from topology or even differential geometry, you generally expect your quotient morphisms to have nice properties. And so the first thing that goes wrong in GIT is that you don't always get a morphism from X to the quotient, which is what you probably would expect. And it's easy to see what can go wrong. If all of your G invariant sections vanish at a point, well, we don't get the point 0, 0, 0, 0 in projective space. So that's going to be a problem. Okay, so we get around that by making a definition. You define what's called the GIT semi-stable locus to be the set of points where you've got at least one non-vanishing invariant section. Okay? Then you do get a morphism from the semi-stable locus down to your quotient. Okay, so we solved that problem by defining it away. The second issue is that you probably expect your quotient spaces to be orbit spaces. So in other words, the points in your quotient should correspond to the orbits by your group action. And that doesn't always happen in GIT. So here, the equivalence relation we get is that two points get identified in the quotient if the closures of their orbits intersect. Okay. So in GIT, the two major questions that we're looking at for any given problem are, what is a semi-stable locus? In other words, when do you have at least one non-vanishing invariant section? And then, when two orbits come together in this unexpected way, can we describe what's happening there? Okay, so let me just quickly mention some open questions about Mukai's model, and there's lots of them. So very little is known. I did see in a paper by Farkas and Vera around 2014 that they have an argument that a general integral curve, so irreducible, with up to 6 nodes is GIT semi-stable. Okay, so we know there are some semi-stable things, and we know that irreducible curves with a small number of nodes make it in. In some earlier work that I gave a Zoom seminar about, I presented some additional examples. I can't actually prove that they're stable for SO10, but I can at least prove that they're semi-stable for a maximal torus in SO10. And some of the singular examples that I considered there include a curve with 7 cusps, and also something called a balanced ribbon, which is generically non-reduced. So I've known for a while that there were some singular things in Mukai's space, but I still don't have anything like a list of the singularities that are allowed. So let me just mention some of the questions that I'm interested in, and I hope that over the next several years, you'll see a series of Macaulay 2 packages and preprints from me answering some or all of these questions. So first, I'd like to know, what schemes can you get by intersecting the orthogonal Grassmannian with a sixth plane. Okay, I'm not quite sure. I have some ideas, but nothing like a complete list. What are the GIT semi-stable points, and how do the orbits come together when they do? Since I'm a former Kirwan student, what's the cohomology ring of the quotient? What's the homogeneous coordinate ring? Or in other words, what is the invariant ring in this case? And then finally, besides just studying the GIT quotient in isolation, you'd like to know more about the birational map between it and M7 bar. So for today's talk, I wanted to do some new work. And so I decided to start studying a family of nodal curves. So this is a highly degenerate family of curves. Here we're looking at the dual graph. So each vertex in the graph corresponds to an irreducible component of my curve, which is meant to be P1. And each edge in the graph represents a node between two irreducible components. Okay, so I'm going to study a whole family of curves. A general member of this family is going to have 11 irreducible components and 17 nodes. And you can see that this graph, which is non-planar, is mostly trivalent, except at one vertex, which I labeled 3, 4, because when it specializes, those two vertices are going to pull apart. Okay, so by the way, I copied that graph onto the board so that you can continue looking at it even after I flip ahead to future slides. Now, I mentioned that this actually represents not just one curve, but a whole family of curves. How do you get that? Well, if you look at component 3, 4, let's see, how do I, oops, I forgot how to highlight. So you'll see that there's 4 nodes or 4 edges that meet the vertex labeled 3, 4. And that vertex is a P1, so you have 4 points on P1, and you have a cross ratio between 4 points on P1. And so as you vary the cross ratio between those 4 nodes, you actually sweep out a whole one-dimensional family of curves that all have this dual graph. That family has 3 specializations where you break that P1 into 2 P1s by adding 1 more node. And then by adding 1 more edge to this graph, you'll actually get trivalent graphs. Okay, so let me show them to you very quickly. So the first one I call G0. And so you can see I took component 3, 4 and I split it apart in the horizontal direction. And then since I'm a good algebraic geometry, the other ones are labeled G1 and G infinity. So here we pulled apart 3 and 4 in a different direction. And here is the last specialization. Okay, so let me just go back and make sure I said everything I needed to. Right, so we've got a family of curves, and it's got 3 specializations to trivalent graphs. Bayer and Eisenbud actually have a whole paper on what they call trivalent graph curves, and so I'm able to apply their results to the specializations. Okay. Does everybody feel sufficiently well oriented to this graph? Yeah. Oh, we'll wait for the mic.
Can you tell me again what the nodes and edges of your graph represent?
Yes, yeah. So when people talk about dual graphs of curves, the nodes represent irreducible components. And for me, in today's lecture, all of the irreducible components will be isomorphic to P1s. And then the edges in the dual graph represent nodes between components. Yeah. Okay, so moving ahead. Why study this family? Seems kind of bizarre. So let me explain why. These are singular curves, but they all do have a dualizing sheaf, and it's very ample for every member of this curve. So it makes sense to think about these as canonical curves. Next, for a general member of this family, either when you're looking at the version that has a 4-valent node, or if you're looking at G0, the corresponding Bayer-Eisenbud graph curve is general in the sense of Mukai's paper. It has no G12, G13, or G14. And on the other hand, if you look at the other 2 specializations, they do pick up G1 force. And so for me, this was meant to be as an example that would be computationally tractable and maybe tell me what's going on in Mukai space as a family acquires a G1 force. By the way, I know there's some combinatorialists in the audience, so I'll just mention how can you see that in terms of the graph. So start with graph G0, it has girth 5, and that's telling you that there's no G1Ds where D is small. And even in GT, the only 4 cycles pass through the 4-valent vertex, so we're still okay. If you draw the other 2 specializations, though, you'll see that there are some 4 cycles, and you use those to build line bundles that give you the G1 force. Okay, so I have written some code in Macaulay 2 and some code in Magma to do several steps in my hoped-for program. So first, I can write equations for this family in P6. I started with the trivalent craft curve given by G0. I used Byron-Eisenbud's algorithm to write equations for it. Then I took components 3 and 4 and swapped out those lines for the quadratic that meets the rest of the curve at 4 nodes, and bang, I have my family. Next, I wrote code to compute the spin embedding of this curve. So my family is made up of a whole bunch of lines. So I parameterized each line. I compute the spinner associated to the Lagrangian given by a general point on each line in my family. And so I was able to embed each of my lines sort of individually into P16 or P15. Now I had the ideal of my curve in P15, and so I just look at the degree 1 forms there, and that gave me the linear space that I needed for a general curve. And now I can start studying limits, either in the flat limits in the Hilbert scheme or limits in the Grassmannian as I approach the specializations. Okay, I will stop short of answering my full question though. I can tell you what the limits are in the Hilbert scheme. I can tell you what the limits are in the Grassmannian. I can't tell you what the limits are in Mukai's quotient yet. And I'll explain why in a few slides. Okay, so first, if you're looking at a general member of this family or at the specialization that I called G0, everything works beautifully. All right. The spin map gives you an embedding into P15. Again, that's not covered by Mukai's theorem, so that's a new result in and of itself. The embedded curve is given by the intersection of the orthogonal Grassmannian with a P6. And I can even compute that those are T-stable, at least for maximal torus in SO10. And in future work, I hope that I can extend that to all of SO10. I think that's probably true. All right, what about the specializations? So first, let's look at the flat limits in the Hilbert scheme. Okay, so I'm looking at subvarieties of P15 that have the degree and genus you would expect of a genus 7 canonical curve. Okay, so for one of my specializations, the one that I called T equals 1, the flat limit is actually the graph curve you expect. Okay, it just isn't the intersection of the orthogonal Grassmannian with a 6th plane anymore. Okay, so that seemed like things were going wrong in a very mild way. On the other hand, at this specialization that I called T equals infinity, things are a little bit weirder. We actually have 3 pairs of nodes coming together to form 3 spatial triple points. So that's the type of singularity that I haven't seen before in work on birational geometry of moduli spaces in the log minimal model program, aka Hassett-Kiel program. So that seemed much more severe. Also, weirdly, the component that I labeled vertex 3,4 didn't split into 2 lines in the way that I expected it to. Okay, so it was easy to compute and study the limits in the Hilbert scheme. What about our limits in the Grassmannian? All right, so this was highly unexpected. You start to get surfaces instead of curves. Okay, and here I wrote out what happens in words, but I think it's easier to show you this picture instead. So in the limit in the Grassmannian, as we approach T equals 1, you see a bunch of surfaces that are either spans of 2 lines or scrolls on 2 lines. And basically, because we're not letting the quadrics degenerate, the quadrics that define the orthogonal Grassmannian can't pick apart these components anymore. And so in the Grassmannian, you're seeing a collection of surfaces instead of a collection of lines. And so I found the limit in the Grassmannian, but I also computed that it's not GIT stable. So Mukai's quotient is actually replacing this by something else, and I don't know what that is yet. And then finally, what about t equals infinity? Here, it's not quite as bad. I didn't draw a picture for this one. Here, you only pick up 1 surface instead of 5. But the degeneration is perhaps even a little more severe. We have 4 lines falling into a P2, which is unusually small for the, compared to the rest of the family. Once again, yeah.
When you say that Mukai's quotient replaces the something else, do you have a notion of a universal family for Mukai's quotient, or what?
Sorry, all I mean is there's this result that people call GIT semi-stable replacement, but it's just the observation that GIT quotients are projects, so they're complete. So you know, I have a family, the general member is stable, so you know, the central fiber has to go somewhere. What is it? And since the obvious limits are unstable, the answer is, well, it's something else, but what? Okay, so that's actually nearly the end of my talk. So open question. I thought when I was completing these calculations that I was hoping these would be semi-stable and they would be the answer, and the talk would conclude by saying, here's what Mukai's model does, but instead it's a question. What does Mukai's model do? All right, thank you very much.